Hello everyone, my name is Parham Dehghani. I'm honored to receive the IAFSS Best Thesis Award for the Americas. Today I'm going to present the essence of my thesis, titled as Using a Gas Supplied Burner to Obtain Flammability Maps of Solids and Liquids in Microgravity in a Quiescent Ambient and without any external radiation. I invite you to read more details from the corresponding papers and let me know your thoughts and/or questions. The thesis was directed by my advisors, Drs. James Quintieri and Peter Sunderland. Before I begin with the technical part, I would like to acknowledge the great team that I had the once-in-a-lifetime opportunity to work with, especially my advisors. The UMD advisors were Drs. Quintieri, Sunderland, and Dres. I am also thankful for the helpful discussions and meetings with Drs. Baum and Senegrev. Also, I would like to thank my dissertation and proposal advisory committee from Fire Protection and Mechanical Department of University of Maryland, and also the NASA team. I give my warm regards to the FSRI team at Columbia, Maryland, especially Drs. Kerber, Majikowski, and Horn. The final corrections of my thesis based on the advisory committee comments and the last paper's analysis and writing, the flammability maps of condensed phase materials in microgravity that was published in at Combustion and Flame, which was the pinpoint and closure to this exciting research project, was accomplished in the time I worked at the FSRI, and I wouldn't be able to close the loop without their support. Okay, so now let's go to the interesting part. The experiment was the result of a great collaboration between the UMD and NASA team. The experiments were automated and controlled from NASA Glenn's Operations Center. The UMD team was responsible for providing the test matrix and detailed test parameters, such as fuel and inert flow rates, camera settings, igniter position, etc. A total of 69 parameters were to be submitted 3 days before each experiment day. Also, we were responsible for monitoring the tests and adjusting the parameters accordingly if needed on the fly. NASA team prepared the experimental apparatus, prepared the communication software with the ISS setup, reviewing the test matrix and parameters, and supporting with the analysis of the data. The outcome of this collaboration was a great data set containing imaging and non-imaging data. This research was supported since the fire behavior in microgravity is not sufficiently analyzed to address the safety of spacecrafts, and the urgency of initiating such project was due to a fire on the Russian Mir space station. The burning rate emulator, which is a gas-supplied burner, provides a cost-benefit and effective approach to examine the flammability of solids and liquids in normal and microgravity. The current project was focused on flames ignited and grown in the quiescent ambient and without external radiation. The main objectives of the project were first, identifying the burning conditions in microgravity that allows steady burning in a quiescent ambient and without external radiation as a function of ambient conditions like ambient oxygen mole fraction and pressure and fuel properties. And second, development of an algorithm to predict flammability maps in microgravity, like flammability of real materials, based on classical diffusion flames theory, and include radiative heat loss to the existing theory through remote radiometry, like radiation measurements. The hypothesis is that the condensed phase fuels burning can be emulated using a gas fuel supplied burner if, first, the flame reaches steady state so that the prescribed burner flux represents steady flame's fuel vaporization rate, and second, the derived heats of gasification and heats of combustion are matched with the properties of the corresponding real material. These two properties, naming heats of gasification and heats of combustion, are the primary significant properties used for emulation. And finally, if the secondary significant properties of laminar smoke point and surface irradiation are also matched. The burner-derived heats of gasification is obtained by heat flux measurement at the burner surface and dividing by fuel mixture mass flux. The delta HC, or heats of combustion, is controlled by varying the nitrogen content of the fuel mixture. For example, if we have a mixture of nitrogen and ethylene with 50-50% by volume, it would yield heats of combustion of 23.6 kilojoules per gram of fuel mixture. The smoke point is applicable to normal gravity flames only and not to the microgravity ones, since those flames are sootless. The three figures show successful emulations in normal gravity for methanol, heptane, and PMMA respectively from left to right. As shown, the burner simulates real material flames on the earth, and the left snapshot of each figure is the real fuel burning, and the right snapshot is the gas burner flame. The missing part in the analytical solution of these flames was radiative heat loss, or radiative loss fraction. Remote radiometers measured flame radiative heat flux, which was corrected for the burner re-radiation and radiometer angular orientation. The sensor distance with the center of the burner was 20 centimeters on average, and compared with typical flame heights of 10 to 15 millimeters, the sensors were considered far enough that the flame could be treated as a point source, and total radiative heat loss was calculated by emittance from that point source to the 4 pi directions. The sensors represents a point on the sphere around that point source, and the heat flux is multiplied by the surface area of that hypothetical sphere, like 4 pi times distance squared times measured heat flux. Now let's take a look at the analytical part. The analytical solution associated with the BRE flames in microgravity is based on the classical diffusion flames theory. The mentioned computed radiative heat loss fraction is incorporated through correction in the heat release rate term, like delta HC. It allows computation of flame temperature, surface average convective heat flux, and flame size, which are functions of the prescribed mass flux, heats of combustion, radiative loss fraction, surface temperature, and ambient conditions like ambient oxygen mole fraction and ambient temperature. And as shown in the video, the dashed line, which is obtained from the analytical solution, can predict flame size pretty accurately. Now I want to switch gears and start showing the results, starting by imaging data. The image sequences are made by using high-quality images. 5 typical flames are shown. The fuel used is ethylene diluted with nitrogen, and the burner was 25 mm in diameter. The two left image sequences represent steady flames at 34% oxygen in the ambient that burned for more than 3 minutes before the fuel was shut down intentionally and led to emulation of PMMA and nylon. The third and fourth one show two self-extinguished flames in 27% oxygen, with high mass flux, low delta Hc, and low mass flux with high delta Hc. Different flame behaviors was observed before self-extinction, like oscillations like flame swirling around burner axis, partial extinction and reignition repeated several times before self-extinction, flame base lifting up from the surface, and flame opening from the top. The last image sequence represents flames that ended with quasi-steady condition, but their heats of gasification and heats of combustion were not matched with real fuels and thus did not lead to emulation. The introduced theory also allows calculation of average surface convective heat flux. The radiative heat feedback is calculated by using a geometrical view factor of the burner with respect to the flame sheet. The geometrical view factor represents the ratio of the total radiative heat loss that impinges the burner surface. The view factor of the burner surface with respect to the flame sheet is the ratio of surface area times the view factor of the flame with respect to the burner surface area, which is also known as the radiation view factor reciprocity rule. And because the latter view factor is equal to 1, the view factor of the burner with respect to the flame, which is the quantity that we want, is equal to the ratio of their surface area. The re-radiation is calculated by using the surface measured temperature. When the heat flux components, convective, radiative, and re-radiation are summed up and divided by the burner mass flux, the L, or heats of gasification, can be predicted. So far, we showed how to predict surface average convective heat flux from theory and surface average radiative heat flux from remote radiometry and some algebraic work to calculate the geometrical view factor, which together leads to calculation of heats of gasification. The most recent and significant outcome of the study is the flammability maps of solids and liquids in microgravity. Note that we showed how to compute flame height, flame temperature, and surface convective heat flux by incorporating radiative loss fraction, and how to calculate the average radiative heat flux by using an algebraic manipulation based on the view factor of the burner surface with respect to the flame sheet. The summation of these components led to calculation of heats of gasification. The heats of combustion also is controlled by the inert fuel mixture ratio. Like I mentioned before, 50-50% mixture of ethylene. Nitrogen yields delta Hc of 23.6 kJ per gram. The basis for finding the flammable region is utilizing a critical temperature for flame extinction, for example 1100 K, which is widely used for microgravity flames. When calculated flame temperature falls below the critical value, it means that no sustained flames could exist under the given condition. On the other hand, if the calculated flame temperature for the given condition is above the critical value, the flame can reach steady state. As shown in the flammability plot, as delta HC versus heats of gasification, or L, when the critical temperature criterion is applied, the two roots of the equation is found. The one associated with the smaller L is referred to as radiative extinction limit, and the other one is referred to as small flame extinction limit. At the radiative extinction, flames get large, that the radiative heat loss is increased and the flame temperature drops below the critical value. And at the other extinction limit, flames are small and the heat loss to the burner surface causes temperature to drop. Therefore, the range indicated by the red font is between the two limits and is the flammable zone. The extinction zone is shown by blue fonts and is located outside the flammable region. The convective extinction limit is a theoretical limit where flames do not have radiation, like chi sub r equals 0. It was observed that extinction happens in a range of critical values where critical temperature is somewhere in between 1100 to 1200 kelvins. The higher limit causes the extinction limits to move towards each other and the flammable zone gets smaller. The two plots represent the flammability maps for the two limits of the critical temperature. Also, it is shown that the ambient oxygen concentration affects the location of the extinction limits and the flammable region accordingly. The flammable zone is inversely proportional to the ambient oxygen mole fraction. As shown, the black lines represent extinction limits of 40% oxygen, and the red curves correspond to the 26.5% oxygen in the ambient. The NASA atmospheric exploration includes enrichment of ambient oxygen and reducing pressure. The ambient oxygen mole fractions used were 40%, 34%, 26.5%, and 21%. No steady flames were observed in the atmospheric condition. Note that the mentioned values of oxygen mole fractions are nominal and the real values were slightly different. The plot shows the flammability map for ambient oxygen mole fraction of 34%. The solid symbols are steady burner flames and the hollow symbols correspond to self-extinguished ones. As shown, the steady flames fell between the extinction limits and the extinguished ones are located in the outside. Therefore, the extinction limits were able to accurately predict the flammable zone. The practical usage of the flammability maps is shown by this plot, where real material properties are superimposed to the flammability maps. For example, polypropylene with delta HC of 43 and L of 2 is flammable in the enriched ambient with 40% and 34% oxygen, but it is located at the extinction limit for the 26.5% oxygen. We have suggested to NASA to use the NASA Test 2, the cone calorimeter, to get the material properties and use the flammability maps accordingly. The BRE burner can be used to emulate condensed phase fuels both in normal and microgravity conditions. The 25mm burner supplied with ethylene mixture with nitrogen was used for these series of experiments. Steady flames were observed at the oxygen mole fractions of 26.5 and above. All flames that were ignited in the ambient with nominal oxygen mole fractions of 21% self-extinguished within 40 seconds. Ambient pressure had minimal effect on the flammability of materials. It affects flame emissivity through changing the combustion product, partial pressures of water vapor and carbon dioxide. A dimensional analysis of the radiation data based on the radiation theory led to radiative loss fraction correlation with the dimensionless parameter omega that allowed prediction of the quantity of radiative loss fraction. A flammability map as a plot of delta Hc versus L, like heats of combustion against heats of gasification, was presented for several oxygen mole fractions. Two extinction limits based on setting the flame temperature to a critical value of between 1100 to 1200 kelvins were obtained theoretically: radiative extinction limit and small flame extinction limit. Thank you for your attention.